The purpose of this lab is to analyze the motion of an object that falls with the effects of drag. Drag, in this lab's case, is the air resistance force on the falling object represented by the formula -b times velocity squared times v hat. Therefore, the object will experience the force of gravity in the down direction and the drag force in the direction opposite to the object's velocity. To observe these forces, I recorded a balled up piece of paper falling from rest, and I wrote code to simulate the object falling from rest once with only the force of gravity and another time with the effects of drag. In the end, I found that my models show the significant effects of drag on an object in motion. For the real-world model, I used a balled up piece of paper for my object and a meter stick to measure its position throughout the video. The system would be the paper ball and the surroundings would be the air and the floor. The ball was dropped from rest at a little over a meter from the ground. Once I recorded the video, I used a software called Tracker to record its position over time. For the computational models, I edited pre-written code of a simulated object and its motion. First, I edited the code to replicate a situation where the only force acting upon the object was gravity. For the second computational model, I added the force of drag to the equation. After collecting the position versus time data from the video I recorded, I saw how the object's velocity would move in the negative y direction. This is to be expected as the gravity accelerates the ball downward. In the latter half of the data, the velocity appeared to be more constant until the end. This must be because drag is proportional to the square of the object's velocity. As the magnitude of the velocity increased, so did the force of drag. To simulate a falling object which is only under the influence of gravity, I would need my net force to be only a vector of mass times acceleration due to gravity in the y component only. The velocity would be updated each time step by adding the net force divided by mass times the change in time for each time step. The object's position would be updated each time step by adding the ball's current velocity times the change in time. The resulting position versus time graph showed an object with constant negative acceleration. To simulate a falling object with both forces of gravity and drag, I needed to add the formula for the force of drag to my net force equation. The force of drag was calculated in my code by multiplying the square of the velocity's y component by the negative of the direction of the object's motion, and then multiplying that by a proportionality constant. With the addition of this force to my code, the resulting position over time graph shows changing velocity at the beginning and more constant velocity at the end. By comparing all the models together, it is easy to see how the computational model with drag better represents the real-world data than the computational model without drag. They both show negative acceleration at the start and then constant velocity towards the end. This could be explained through the formulas of each force acting on the ball. As the magnitude of velocity increases, the force of drag is able to compete with the force of gravity, bringing the net force closer to zero and making the velocity of the object constant. During the collection of data, there might have been a few cases of error. The meter stick might not have been perfectly parallel to the motion of the ball, and when measuring the movement in Tracker, I may not have perfectly recorded the correct position of the ball at each time step. Which models show a presence of terminal velocity? Terminal velocity is where the force of drag equals the force of gravity. As discussed before, the real-life model and the computational model with drag shows terminal velocity through its unchanging velocity towards the end of the data. When the force of drag equals the force of gravity, the net force on the object is zero, because the force of drag points in the opposite direction of the force of gravity. What if the object had an initial negative velocity? If the initial velocity started as less than zero, the object would be closer to its terminal velocity. The formula for gravity is not affected by the object's velocity, while drag is. I used my code to test this idea by changing the initial velocity in the object to -1 in the y direction. In the end, this lab shows how the behavior of motion can be better predicted when acknowledging the effects of more factors such as drag.